give you a trick?
Sure.
Hit F5, you don't have to look around for any menu or anything. Sweet, huh?
I'm Stephanie Rolston. I'm from TAN Group, and we are doing the duct cooling for our system. And this is going to be our results for the steady state operating curves and for the step function. The duct cooling system is a single input, single output system, like you see in the schematic over here. The hot water enters the system, and the step input is how much of the motor power is used to cool the water, and that will determine how quickly the water is cooled. The input is the manipulated variable, and for this experiment, the input percentages for SSOC were constant for each trial, and they range from 44% to 70%. And for the step response, the input was not constant and for each trial, but the change in percent input was constant. We did either plus or minus 20%. And for that one, the inputs varied all the way from 25% all the way up to 98%. The output is the control variable, and for the output range for both the SSOC and step response experiments were to be between 44 and 56 degrees Celsius. Okay. Just a little bit more about steady state operating curve. For each value of the input variable, there's obviously going to be a single output. To make the curve, we plot the input function on the x-axis versus the output on the y-axis, and that makes the curve. We obtain this by taking measurements at the varying inputs. For the steady state operating curve, our outputs were to be 44 to 52 degrees, and we used inputs 44 to 70%. Heater 1 we had on, and heater 2 we had off. Measurement was taken, we could either take it in the middle or at the end. We chose to take it in the middle, and both of our dampers were closed and trial length laid. This is the curve we obtained for the output is going to be equal to a negative 0.3894 times the input. And for the step response, it's going to be a transfer function, which is going to be the ratio of the Laplace transform of the output to that of the input. This only applies to linear time invariant differential equation systems, which would be the system, and this gives a full description of the dynamic characteristics of the system. Okay. For the step response, we had the same temperature output that we wanted, and we had inputs varying from 25 to 98%. Again, heater 1 on, heater 2 off, measurement taken from the middle, and both dampers closed. And our step was plus or minus 20%. Okay, for the results for our gain, the lower step for the lower input range had the largest error, but you can see that it as the for the higher ranges we have a much less much smaller gain. For dead time, the dead time depended on how long the trial was overall, because it varied so drastically with how long it was in steady state. For our time constant, the lower down step, with the exception of the lower down step, it appeared that everything was increasing linearly, but again we had a large amount of error on that one. Overall, our results are for the gain for lower, mid, and higher up steps were 1.2, 0.6, and 0.3 degrees per percent. And for the down steps, it was negative 0.9, negative 0.2, and negative 0.1 degrees per percent. Dead times, like I said, didn't really seem to have a whole lot of rhyme or reason without the consistent input or consistent trial time. So they ranged all the way from 0.3 to 1.6 minutes, and for the up steps, or for the down steps, range from 1.2 to 2.3. Time constants for the up steps, they increased as the input increased, and for the down steps, they time constants decreased as the decreased with it. We can conclude from this that the magnitude of K is larger with a lower input and decreases significantly as the input increases, and with the exception of the lower down step, as I mentioned before, the time constant increases in a linear manner with the increasing input. And the dead time is mostly dependent on the length of the trial. The longer the trial, the longer the dead time. And that's it. Okay. And would anyone have any questions?